Hello everyone, my name is Dan the Tutor, and today we're going to be continuing our talk about limits, and specifically we're going to be looking at something called limits at infinity. It does not take a genius to figure out we are talking about something with limits and infinity. So limits at infinity. And here's why limits at infinity are different than your run-of-the-mill limits. Here's why. It looks something along the lines of this. Limit as x approaches either plus infinity or minus infinity of some function f of x. So for instance, x plus 1 over x squared minus 1. This would be an example of a limit at infinity, and I will tell you what this means. If you were to plug in infinity into the function, so look at how you would solve this limit before. We would either use direct substitution. Well, actually, if you think about using direct substitution here, it's kind of funny, right? Like, how would we plug in infinity for a function? Well, here's what it would look like if we did direct substitution, right? We would say infinity plus 1 over infinity squared minus 1. And it's kind of like, well, what does that even mean? What does, how would I even think about computing that? And that's why there are some rules that we need to know about limits at infinity and just plugging in infinity in general. Here are some rules of infinity, okay? Infinity plus 1 is still equal to infinity. Infinity plus 1 million, though, that's still just going to be infinity. So you can add any number to infinity, it's still going to be infinity. You can also have something like 2 times infinity, and that's still going to equal infinity. You could also have 100 times infinity, it's equal to infinity. You get the picture here. The only time where you can really make infinity bigger is by saying if you have infinity squared. And I'll tell you, infinity squared is greater than regular infinity. And similarly, infinity to the 42nd power is greater than infinity to the 41st power. So really, it all depends on how many infinities you have. The bigger infinity you have, the bigger number you're going to have, okay? And another thing to think about is this right here. What's 1 divided by infinity? I want you to think about this. What's 1 divided by 100? 1 divided by 100 is 0.01, right? What's 1 divided by 1,000? That's going to be 0.001. What if you had 1 divided by 1 million? What if you had 1 divided by 1 million? You'd get 0.000001. And as you can see, as you keep building, making that number bigger and bigger in the denominator, you keep getting a smaller and smaller number, like 0.000001. You keep getting closer and closer to 0. And to the point where you actually plug in infinity into the denominator, you're actually going to get 0. So 1 over infinity is 0. 1 million over infinity is still 0. It doesn't matter what it is. If you're dividing by infinity, you get 0. And the only time where things get a little hairy is when you have infinity in both the numerator and the denominator. And so here's how we're going to discuss this, okay? I will tell you, infinity divided by infinity is kind of a weird case. It's called indeterminate. We're going to talk about that later. But if you have infinity over infinity squared, well, remember, you can think of it like this. You can think of it as one of the infinities canceling out with each other, and you're left with 1 over infinity. And if you remember the other rule, 1 over infinity is just 0. So whenever you have a bigger power in the denominator, that's just going to be 0, if you think of canceling it out. Another situation you could have is where you have infinity squared divided by infinity. And in that case, again, you can cancel out one of the infinities with 1 infinity in the denominator. And in that case, you would just get infinity. And so one thing that's kind of interesting then is in the example we just saw, x plus 1 over x squared minus 1, if we were to plug in infinity here, that would become infinity plus 1 over infinity squared minus 1. And remember, the plus 1 and the minus 1 really don't matter here, so I can even cross them out for this case. And we see the infinities cancel out, and we get 1 over infinity, or 0. And so back to the very initial question when I asked, what is the limit as x approaches infinity of x plus 1 over x squared minus 1? That limit is going to be infinity, and if you remember anything about limits, if the limit is ever equal to infinity, we have to say does not exist. If the limit approaches infinity, we say it does not exist. And now we're going to talk about some shortcuts so you can easily look at a polynomial divided by a polynomial, which polynomial is a fancy word for something like this, where it's just a string of x's. raised to some power, and then, a constant at the end sometimes. But we can talk about how to find those limits very easily. And so just in general, if I have some limit as x approaches infinity of 4x cubed minus 5x squared plus 10x minus 2 divided by 3x squared minus 10x plus 4, how would we find this? It's going to take a ton of time if you just keep writing infinity and infinity for all these points. So really what you're looking at here is the highest power of derivative, the highest power of infinity that you're going to be plugging into. And in the numerator, it's 3. In the denominator, it's 2. And since 3 is greater than 2, in other words, the degree of the numerator is greater than the degree of the denominator, then we're going to get infinity, which does not exist. And that's because the power is higher in the numerator than it is in the denominator. How about now, limit as x approaches infinity of x squared minus 5x minus 10 over x cubed plus 3x squared minus 5x plus 1/5. The numbers really don't matter. All that matters is the leading degree, and in this case, the numerator is 2, and that's less than the denominator, which is 3 for the degree. And so what we can say then is that the limit is just 1 over infinity, which remember is 0. And this one does exist. Like 1 over infinity exists because it's 0. The answer is 0. It's not infinity. So before, when the limit was infinity, we said did not exist, does not exist. When it's 0, when the final answer is 0, that's a perfectly acceptable answer to have. And now, one more case, again, this is the annoying case, when it actually equals each other. So limit x approaches infinity of x squared plus 5x plus 4 over x squared, I'll say 2x squared minus 2x minus 2. And in this case, they're equal to each other, right? Numerator 2 is equal to denominator degree, which is also 2. And in this case, they're not going to cancel out exact. Here's what it is. This has a 1 in front of it, if you want to think of it like this, okay? And what you're essentially getting here is 1 infinity squared over 2 infinity squared. Think of it like the infinities canceling out, and all you're left with is a 1/2. 1/2 is the answer to this question. And so whenever you see the degrees match each other, they're equal, you need to look at the coefficient to determine your answer. And now there's one more thing I do want to say about limits at infinity, and that is how limits at infinity are the exact same question as what are the horizontal asymptotes for a function. Do you remember what horizontal asymptotes are? Those are the dashed horizontal lines on your graph that says the function is going to approach but never touch that line. Like if that's that, and we have some function that looks like this, then that line is going to get really close to whatever that value is but never cross it. That is actually what a limit at infinity is. And so to give you an example, here's the function f of x equals 1 over x. This is what it looks like. It looks like this on the right, and it looks like this on the left. And if you remember, it's going to have a horizontal asymptote as well as an asymptote at 0. Now, let's think about what that means in terms of limits. Like if I ask you to find the limit as x approaches infinity of 1 over x, remember that would be like 1 over infinity. The degree of the denominator is greater than the degree of the numerator, and so we just get a limit of 0. And so the limit here is the exact same thing as the fact that we have an HA, a horizontal asymptote, at y equals 0. So we see here that the limits at infinity match the horizontal asymptotes of your function. Don't worry about the vertical asymptotes, that's not what this is about. You can use limits at infinity. Limit as x approaches infinity or negative infinity will give you your horizontal asymptotes. What about the case where you have limit as x approaches negative infinity? 5x plus 1 over 3x minus 2. Okay, in this case, we have, if we were to plug in infinity, remember these have the degree of the numerator is equal to the degree of the denominator, which means the way we would solve it is by looking at the coefficients. The answer is going to be 5/3. I'm telling you that right now just by using the shortcut method. If you wanted to actually do it the plugging in infinity method, you would get 5 times negative infinity over 3 times negative infinity. And you can see here that the infinities are going to cancel out with each other perfectly. Even though it's negative infinity, it's still going to be 5/3. And so the only time you have to worry about negative infinity ever is really in the case where the numerator is greater than the denominator. You can have the case limit as x approaches negative infinity of 3x squared plus x over 5x or something like that. And what we would have here is degree of numerator greater than degree of the denominator, because degree of the denominator is just 1. It should be approaching infinity. However, think about what's going on here. We essentially have 3 times negative infinity squared divided by 5 times negative infinity. Only one of the negative infinities are going to cancel out, and so we're left with 3 times negative infinity over 5. The 3 and the 5 don't matter. It really is just going to be negative infinity. So the limit here is negative infinity, but remember, this also doesn't really matter because as soon as we see infinity or negative infinity as our final answer, we're writing does not exist anyway, DNE. And so that's really the answer to our question here. So the point of all I'm trying to say here is that if you see negative infinity, don't freak out. It's pretty much going to be the same answer either way. And that's pretty much it. So thank you for joining me. My name is Dan the Tutor, and I'll see you next time.